Okay, so good morning, everybody. So today I will introduce our product, ID Explore. It is an open access based software. It represents a constraint-driven design methodology, both for analog design and migration at the simulation level. So I will present first the mission of Intento design, then we will try to open the holy grail of analog. We will describe the Intento design approach and what is the concept of incremental design. And then we will show an industrial case that we made. And then we will try to position ID Explorer in the ecosystem. So as you see in the logo, Intento design means design by intentions. It means that the designer has to express his electrical constraints. And based on these electrical constraints, we have a responsive EDA that will react based on these constraints to give him the correct sizing and biasing very quickly. So today, Intento design develops and commercializes ID Explorer to accelerate analog design, but more important, to accelerate technology migration. So here I present the flow of the traditional design flow of analog on the left, and on the right we present the Intento design flow. So let's see what is different between these two different flows. So on the left we start with a schematic entry, and then we followed by a test bench entry, and then we enter into an iterative process. We enter into an iterative process here that can be thousands of iterations, and it depends on the complexity of the design. Once we get the size and bias correctly, we put them into open access database, we go through Excel, and we validate the performance. The flow of Intento is a little bit different. We start by the constraint editor. We document DC constraints into open access database. We have a traditional design entry of the test benches, and then we go to our tool. Our tool uses this constraint to quickly size and bias into the open access database. We don't have a loop here, but we can communicate with the spectr. In a very few calls, we can get the size and biases. The main point of migration is that we can map these sizes and biases to from any PDK. So we can have the same DC constraints that map the sizes and biases coming from any PDK. The particularity of this flow is that we can ensure that the design is correct by construction by comparing the output of ADXL and comparing the performance output from our tool. If both are coincident, it means that this IP is correct by construction. Otherwise, we have to review the design. So since the 1980s, lots of researchers tried to develop analog synthesis tools inspired from digital, and there are a lot of questions if computers can really prove the formal correctness of analog design, and if at least we can use the net list of transistors as a seamless form for analog synthesis. But all of these questions, unfortunately, we will not be able to answer them. So at Intento, we decided to speak about analog design acceleration rather than analog design synthesis. So in Intento technology, we have identified an intermediate presentation that can represent very fairly the knowledge of analog design. Exactly the same way like control flow graph and data flow graph in digital. And we have supported this intermediate presentation with the constraint-driven design methodology. And as a consequence, we can improve that the design is correct by construction. And moreover, we can give guidance to the designer if the hypotheses he has set are really correct or not, or some hypotheses are conflicting, or some parameters are missing. And I will show an example on this one. So the hope is that the analog designers can really accept an insightful automation. It's not a blind automation. So let us open a little bit the Holy Grail. So in this slide, we have 4 vectors here. Okay, I will try to classify all the analog tools in the market in this diagram. For example, the SPICE-like simulator, it's a mapping from vector 2, which has size and biases, to the performance models. This is SPICE. So lots of research has been done to couple SPICE with a search engine. And we have commercial tools like Neolinear, like ADA, like many others. But the problem is that they were using this vector. And this is not a vector that is very representative for automation. because most of the time these vectors push the optimizer into non-feasible regions most of the time. But the designer does something else. He doesn't use this vector. He uses this vector, which is the design parameter set. They are more intuitive for him. So we can say that there is an automation gap here. This step was never so automated before in analog synthesis, and this is the main cause of failure for this domain, actually. So in Intento design, we were able to develop a constraint-driven design methodology that can deduce vector 2 directly out from vector 1. So the designer can select the topology, select some parameters on this topology to control, and these two information are enough to do this mapping. So we can automate the whole flow from 1 to, and we are much, much faster. But the particularity also of this vector is that most of the time it pushes the optimizer in the feasible region. So let's see how it works. There is a mindset shift a little bit in this approach because simulation-based optimization are using simulators, but simulators deals with matrices. It means that they are doing simultaneous resolution. So if you have an amplifier with 30 nodes, we have 900 elements to compute at each step, iteration, which is a lot of computations. So we decided the graph theory tells us that we can convert this matrix into a graph. So this is what we did. We converted this matrix into a graph, so we have only 4 elements to compute, not 16. So on this simple example, we are 4 times faster. But the more important is that we don't compute this simultaneously. We compute first node 1, then node 2, then node 3, then node 4. So we have a structured resolution approach. So to illustrate the complexity of today's solution and to see why designers cannot go fast, but a big part of the reason is because the tools that you are using doesn't allow them to go fast, like the simulators, SPICE simulators. So what we did is that we took the not Newton-Raphson equation. We just split the Jacobian into L and U decomposition. And then we did X, substitution X by U delta. So we have these two equations. We solve first by X using forward substitution. And then we take X here, we solve for delta V using backward substitution. So we did something simple. We tried to represent this as a graph. And we found that it's a very complex graph, actually. This is what represents the computations of inside the simulator at each iteration. We see here X1, X2, X3, this is the forward substitution. V3, V2, V1, this is the backward substitution. So we have to do forward, backward, and then next iteration. So this is a really complex computational effort. But the designer, in order to use the simulator, he tried to first get an initial guess for widths and lengths. So he does something much simpler. He takes the first order model of the transistor, he computes a width, and then a polarization, and he moved to the second transistor and so on. So we thought about developing a methodology that can, based on this approach, which has a low computational effort, but can benefit from the accuracy of this approach. So we have a fast approach with the accuracy of this approach. So we did something simple. We adopted the same strategy of the designer. So we developed some primitives, and these primitives like X, like logic gates in digital, but it's for analog. It's a complex numerical inversion of the PDK to compute any parameter of the transistor. So we just plug in the PDK to this primitive, and we can compute widths and polarization for the transistor. We go to the next one and so on. So instead of using hundreds and hundreds of iterations, we just use 3 iterations. And since we are solving only one transistor at a time, the Jacobian element here is only 1 element. It's not 9 elements. So, but how it works in reality? So actually, this is the manual design. Here in hand analysis, we have an insight for hand analysis with a very low computational effort. And we'd like to combine it with the actual PDK to have an accurate sizing. So instead of days, we just go for minutes. And we gain all these advantages. For example, we have a robust constraint-driven design and migration methodology that is fast and interactive and deterministic. It's not based on optimization. and it's correct by construction. But more important, it gives the designer full control. And I will show this by an example. Since we have this interlinear representation, we can do an incremental design approach. So we can guide the designer through his journey of developing this IP, if he's going into the right direction or not. And we can free the designer from all laborious tasks, especially migration. Some designers doesn't like to do migration. We can just do it very quickly. So let's see what is the concept. So here we have an unsigned schematic. We have technology constraints that are coming from the PDK, and we have performance constraint. So these three elements are used today in order to do simulator-based optimization. We have added additional two information. The first one is the electrical constraints that are not on the topology. We cannot deduce them from the topology, and they come from the expertise of designer. So the designer has to document this, and this is what I call DC constraints. And we add a design parameter, which are the set of parameters that the designer would like to control on each transistor. We take this, we have a very intelligent tool that takes this and constructs this graph in memory. It's a very simple graph, but it shows exactly how the designer would do it by hand. I will explain. The designer here will try to size M3, followed by M1, followed by M5, followed by M8. And this is what we should get from our tool. We have, we have here M3, followed by M1, followed by M5, followed by M8. So we are capable of deducing quickly what the designer would like to do, and we just do it quickly for him. But we cannot deduce it without the input of the designer. This theory simply tells that if we have a set of DC constraints and a set of parameters, we have only one graph that satisfies both. So more important also that we can just fix, after constructing this in memory, we can just fix the values and doing one iteration, and we get the widths and biases on each transistor, and we get the actual threshold voltage. It's not an estimate, it's an actual threshold voltage. If we do a simulation, we can match this threshold voltage. So what about incremental design? Since we have this graph, we can guide the designer for during sizing. So for example, here we selected to size this differential pair. So we added the constraint in the constraint editor, and we chose to set these two parameters for M1. So we launch our tool. Our tool tells the designer that I cannot build the graph, so I cannot size this analog transistor because there is a missing parameter, excess gate voltage, on transistor M1. So the designer go back in his constraint editor, he adds the excess gate voltage. Now the tool can size this transistor, and it tells him that he can proceed to define his design space. And each time we add a transistor, we construct the increment, the corresponding graph, and so on. So once we get this, we have all the advantages of acceleration and migration. So for example, here we have designed this band gap on X-FAB technology, 0.18 micron SOI. So we got 10 solutions. They don't satisfy the specs, some of them, because the technology is not really adequate. So what we do is that we select one of these global solutions, we push them into a local refinement, so we get a solution here. Once we get this solution, you can back annotate it into cadence, and then we can verify it by ADXL. But we try to take the same design we shifted from SOI to global foundries, CMOS. And here, amazingly, we got the 10 solutions satisfying. So it means that the global foundry for this band gap was better for these specs. So we can just select the trade-off here. For example, we can go and select the solution with the minimum power consumption. We can locally refine it also for better power consumption, for example, and we back annotate it into open access or cadence, and then we verify. So what is the industrial case that we solved? It was at the customer doing RF circuits, and he was using, he has his proprietary class AB amplifier. It was 75 transistors. He wanted to design this on 180 nanometer, and he wanted to push the performance of the speed to 30%. but he couldn't because when he launched our tool, the tool told him that there are already 2 errors in his design. The first one, he was oversizing a transistor to 500 micron, and the tool sized it to 32 micron. So when he did the sizing at 32, he got all the specs very quickly. But he had another problem, is that he had an additional 0 in the AC analysis. He thought that our tool was the reason of this. But when he further pushed the test, he found that the 0 comes from his test bench, not from the IP. So it means that the tool can really give him guidance on what is the problem and how to tackle the problem. So today, this is what we announced in DAC. For this circuit of 75 transistor, if we go into a single core serial version, we can size it into 30,000 seconds. But with these 3 different category of technologies, it's like a gear shift, we can speed up. We go from 30,000 to 170 seconds. We get the same optimal solution in all these trials. And we do it on a standard Intel 4 processor laptop. It doesn't require computational efforts. We can see here, for example, that the 1 core is maybe more performant than the 4 cores on multi-threading. This may be due to overhead in communication and thread management. So today, ID Explorer is really an intersection between design expertise, circuit modeling, and PDKs. So it is the composition of all the mix of all these 3 areas. It can really have added value to all actors for global for foundries, for analog IP providers, for small design houses, for IDM providers, and for SOC fabless. So today we can accelerate analog design, so we can reduce the cost and with faster time to market. But more important, we can liberate the designer creativity from the burden of handling the technology. We can boost also technology migration with all the same gains, and we are compatible with all PDKs and with all types of devices like SOI, CMOS, LDMOS. We tested on power converters, we tested on standard amplifiers, we tested on different PDKs. Now we have some requests to do it on FinFET, which is something quite easy for us. And specifically also it's a form, this is a graph and the database, it's a form of exchange between design teams in a corporate way. It does not mean that the designer, when he uses the tool, we can, between quotations, replace him. We cannot replace him because he is the one creating this knowledge by himself, and he is the one who has to validate each design step and each decision also. So it's a way to help him accelerate his productivity. So thank you for your attention, and I think you can visit us in our booth for demos on these test cases. Thank you very much.